Hi everyone. Welcome to the second part of the introduction to the hypothesis testing. In a nutshell, a hypothesis test proceeds in three steps. You define a critical region W in the space of possible experiment outcomes xvector. You do your experiment. If the observed data xvector ops falls into the critical region, you reject the tested hypothesis. We ended the previous video with an explanation why it is impossible to test a hypothesis without having an alternative. Simply, we wouldn't know where to place the critical region if we didn't have an alternative hypothesis. Once we have it, gentlemen Neyman and Pearson will teach us how to define the critical region in an optimal way. Let's listen to their famous lemma. By the way, have you noticed that groundbreaking discoveries in mathematics are often called lemma? What a nice modesty. The Neyman-Pearson lemma provides a prescription how to choose W such that the resulting test of H0 has the highest power with respect to H1 for a given significance alpha. Let's assume f of x vector given h0 and f of x vector given h1 are PDFs for data given hypotheses h0 and h1. Then W is defined by the following prescription. T of x vector equal to f of x vector given h1 over f of x vector given h0 is greater than C sub alpha. The constant C sub alpha is chosen such that the integral over the critical region W of f of x vector given h0 dx vector is equal to alpha. The idea why the Neyman-Pearson lemma holds is the following. Let's assume we change the critical region W suggested by the two gurus by adding a small region delta W plus and removing another small region delta W minus. The integral of the PDF predicted by h0 must be the same on the two regions because the size of our test is fixed. However, the integral of the PDF predicted by h1 is larger on the region we removed because the ratio of the two hypotheses is larger on the region. This is the Neyman-Pearson's construction. Therefore, the power of the test decreases. The takeaway of this proof idea is simple. Never modify suggestions by giants in mathematics. With the Neyman-Pearson lemma at hand, it seems we are done with hypothesis testing. We have the optimal critical region for outcomes of our experiment. Unfortunately, this is not the end, but rather the real beginning of our chapter, mainly for two reasons. First, it is impossible to get the PDFs predicted by our hypotheses H0 and H1 very often. In particle physics, both theory predictions and modeling of an experiment response are very hard to evaluate analytically. Second, the Neyman-Pearson lemma only works for simple hypotheses. Those are hypotheses without unknown parameters. Unfortunately, if we want to include systematic uncertainties into our test, we need to add three unknown parameters into the test, and the Neyman-Pearson lemma will no longer hold. But don't worry, you will see later that something very similar can be employed in its stead. Both problems are going to be addressed in future videos. In this video, we are just going to give several definitions and remarks that will be very useful for understanding of the upcoming topics. In the Neyman-Pearson lemma, we saw that the critical region in the n-dimensional space could be defined by a simple condition on a one-dimensional function of data t of x-vector. The function can be very complicated, but nevertheless, it is fabulous to reduce the huge dimensionality of the data x-vector into a one-dimensional object. In general, any function of the data is called statistic. Please don't confuse this word with statistics, which is the name of the whole mathematical discipline. A statistic can itself have one or several components, dimensions, but we are going to use one-dimensional statistics in this course. As in the Neyman-Pearson lemma, we are going to define critical regions with the use of one-dimensional functions just by requiring the function to be larger or smaller than some constant. Another term we have to introduce is p-value. In a nutshell, p-value is the probability to find data as incompatible with H0 as the observed data or more. Recall that the compatibility with H0 is judged based on the alternative hypothesis H1. The p-value definition is super clear in one dimension. Then it is typically given by an integral over a certain range. For example, if the PDF predicted by H0 is the red curve, and the alternative hypothesis predicts large x values, then the p-value is the integral from x ops to infinity. In n dimensions, one needs to define hypersurfaces that correspond each to a set of x-vector points having equal compatibility with H0. Then the p-value is the integral of the PDF predicted by H0 over an area delimited by the hypersurface. Just make sure you pick the correct side. Note that under the assumption of H0, the p-value is uniformly distributed. Under the assumption of H1, low p-values are more probable. The PDFs for p-value given H0 and H1 could look like the red and the blue curves. At this point, it is almost crucial to define the significance z. Simply, z is a proxy for p-value. However, this proxy is extremely common, at least in particle physics. When you walk through a CERN cafeteria, you can hear at each table 5 sigma, 2 sigma, 3 sigma, 5 sigma. If you know the significance, the p-value is given by the following integral of the Gaussian distribution. P is equal to the integral from z to infinity n of x with parameters mu equal to 0 and sigma equal to 1 dx. And this is equal to 1 minus phi of z, where phi denotes the cumulative distribution of the standard Gaussian. To convert p-value into significance, we have z is equal to the inverse of phi of 1 minus p. Up to now, we've lived with the variable xvector that denoted the possible outcome of our experiment. Let's discuss very briefly what this xvector can be in particle physics, and let's take the ATLAS experiment at the LHC at CERN as an example. We can think about two extreme cases. X-vector is just a single number, the number of inelastic proton-proton collisions. However, this would be insensitive to almost any physics goal. X-vector is a huge vector of huge vectors, where each component of x-vector stands for one collision of proton bunches, and the component itself, let's denote it y-vector, corresponds to the ATLAS raw data, which is information from 100 million sensors. Such an x-vector wouldn't be possible to handle computationally. Of course, x-vector is something in between. The dimensionality of the raw data is reduced by a computation of high-level variables like number of electrons, muons, photons, jets, their transverse momenta, missing transverse energy, etc. The number of components of the x-vector is reduced by applying event selection criteria. For example, we can require there be exactly 2 muons in an event, the missing transverse energy to be higher than 20 GeV, and so on. In the simplest case, we can define some event selection criteria and just count the number of events that pass them. This is called a cut-and-count analysis, and surprisingly, it is quite common in particle physics. We can use it as a demonstration of what we've learned until now. Attention please. We are going to search for a new particle, the SpongeBob boson, with the use of a cut-and-count analysis. The hypothesis we need to test, H0, is the standard model. Let's assume n sub s is the number of signal events and n sub s is distributed according to a Poisson distribution of n with a mean equal to s, where s is the expected number of signal events. Similarly, n sub b is the number of background events, and n sub b is distributed according to a Poisson distribution of n with mean equal to b, where b is the expected number of background events. Consequently, the total number of events, n equal to n sub s plus n sub b, is distributed according to a Poisson distribution of n with mean equal to s plus b. Recall that the sum of two numbers distributed according to a Poisson distribution is itself distributed according to a Poisson distribution. Let's further assume that b is equal to 0.5 and that we observe 5 events in our experiment, and ops is equal to 5. The choice of the test statistic is simple. We will use the number of events n. Actually, any monotonic function of n would do the same job, but we don't need to make our life any harder. We are testing the standard model, which is the same thing as testing the hypothesis that s is equal to 0. Obviously, region of n with equal or higher incompatibility with the null hypothesis, as n ops equal to 5, is n greater or equal to 5. We are getting the following p-value. P is equal to a sum over n equal to 5 to infinity, b to the power of n over n factorial e to the minus b, and this is equal to 1.7 times 10 to the minus 4. This corresponds to a significance z is equal to the inverse of phi of 1 minus p, and this is equal to 3.6. In particle physics, the size of tests used for discoveries is 5 sigma. Therefore, we cannot conclude that we found the SpongeBob boson.